Today we're really going to get into the idea of thermodynamics. So I want to talk first about what a state is. So, and even before that, perhaps I should define something called an ideal gas. You don't want to mess with regular gases when there are ideal gases around. An ideal gas is a gas, well, a gas is molecules of stuff kind of bouncing around on each other. And an ideal gas means two things. One, they do not interact with each other. So here we go. No interactions. And not only that, but not only do these particles not really interact with each other, I mean, they're going to hit the walls, but they won't really hit each other, but also they don't take up any space at all. Molecules don't take up space. So this lets us do all kinds of approximations. You know that the physical world is incredibly complicated, but we can start understanding gases by disregarding all interactions between the gas itself and saying that the molecules take up no space at all. Now, a lot of gases are pretty good approximations to an ideal gas. So as long as it's not really dense, many gases are nearly ideal, I guess I can say. All right, like air in this room, very nearly ideal. So let's start this idea of equation of state. And I want to talk about what that means. It's sort of like, the president every once in a while talks to you about the state of the union. This is an equation of the state of the system. So it's sort of like saying, hey, what's going on, system? And it talks about how the different parts of the system might interact. So we're going to be talking about pressure in particular today. And from our constant volume gas thermometer, how did this thing look? We had this tube that went way up, and then we filled some gas in there, and we had mercury. We marked this line, and we filled mercury in here. And the mercury came up here, and we could control the pressure by adding or taking away mercury, that dangerous fluid right here, and it was this height that mattered. Remember all that constant volume gas thermometer stuff? I guess what we learned from the constant volume gas thermometer is that if we raise the temperature of this gas, here's this bluish gas in here. If we raise the temperature of the gas, the pressure goes up. That was the cool thing that we learned when we derived the existence of absolute zero. So I'm going to say that from this, pressure is proportional to temperature. More pressure, more temperature. More temperature, more pressure. All right, but what if you think about like a volleyball, and the volleyball is flat and you want to pump it up, right? Yeah, so you want to pump up that sucker, and then the pressure is going to go up. But what have you changed? If you pump up a ball, you have added more air into the middle of it, and we're going to represent more air by capital N. This would actually be the number of molecules. Maybe I could be more specific. Me more general and say number of particles of gas. All right? And I guess that makes a lot of sense. If you double the amount of stuff that's in a certain volume, I guess, maybe we should preface this by saying holding other stuff constant. Yeah, so this is very, very tricky. We have to be careful to make sure that we know that we're holding other things constant. So if we're holding the number of particles the same, and we are in a constant volume gas thermometer, we raise the temperature, then the pressure goes up. But if I took stuff out right here at the same time as I raised the temperature, I could probably get the pressure to stay the same. All right, fair enough. And in this case, if I'm adding more particles of gas, as long as I'm not changing their temperature, then this will be linear. The pressure will be linear in that. What about, though, what about also changing the pressure by squishing this volleyball? As I squish it, the pressure does what? Well, pressure increases, and if the pressure increases when I squish it, what have I done to the volume? Would you say that the pressure increases with more volume? No, that's ridiculous. If I were to, interesting. If I were to decrease the volume, then the pressure would go up. So that means we may have an inverse relationship. I hope you find that reasonable, that this is the volume. And the cool thing about a volleyball is the volume is pretty much constant unless you're actually deforming the sucker. So that's why we can shrink that sucker and get a smaller volume and therefore a higher pressure. So let's put all of this stuff together. And I'm going to come up with this cool equation that says pressure is some constant times the number of particles we have times the temperature and divided by the volume. Or in the more fancy way, get ready, Ben, PV is NKT. And you've seen this before. It might have went with a lowercase n and an uppercase ara, but we can get there. I'm going to take this. This is called the ideal gas law. Let me slap it down for you. Ideal gas law. So I'll take this equation and tell you a new definition. What if I came up to you and I said this capital N, that's the number of molecules, right? It's also, what if I talked to you about this Avogadro's number? This Avogadro guy liked to count really high, and he said, my number is going to be 6.022 times 10 to the 23rd. That's a really, really big number. And I guess it's molecules per mole. Ooh, sneaky. Interesting how molecules and mole both start with the same. You wouldn't want to abbreviate these units. So if you've got the number of particles right here, and you know the number of moles, all you have to do is multiply by the number of moles. So the number of particles is the number of moles times the number of molecules per mole. So we're back to molecules or particles. And this other definition, the other definition that we need is that ara, the ideal gas constant, did I tell you about this K here? This K is Boltzmann's constant. We're often going to call it KB for Boltzmann. And it is on his gravestone. Boltzmann's constant is, oh man, that's some number. You can look it up. I think it starts with 8. No, just kidding. You can look up Boltzmann's constant because I don't have that in front of me right now. But the ideal gas constant is Boltzmann's constant times Avogadro's number. So let's put all this stuff together and make a little substitution. Oh wait. N is really big, probably. If we have a substantial chunk of gas, we're probably going to have billions of particles. And then K is really small. K is actually really small. And, let me put K down here for you. I found K while I was stalling. 1.38 times 10 to the, check it out, negative 23rd. And it's got units of energy per Kelvin degree. Interesting. So let's see if these units work out. We've got number, that doesn't really have units. We've got energy per Kelvin, and we've got Kelvin here. So this is units of energy. So pressure times volume must be unit of energy also. In fact, we found that pressure times volume is an energy. It's a potential energy. It's a stored energy. Because a certain volume has a certain pressure, you could do work with that. Okay, all right, let's go back over here. Come over here with me. Come on. And I want to tell you that PV, that's an R, PV is N, but remember N is lowercase n, times Avogadro's number, and then times K, but we could solve this for K also. This is R divided by Avogadro's number times temperature. So if we simplify this, get a little bit of blue, boop, boop, and we say that PV, yeah, just as you remember from your chemistry class, PV is lowercase n times capital R times T. And I guess all I want to say is this is usually what you'll be doing in physics, this is usually what you'll be doing in chemistry, because physicists like to talk about particles and chemists like to talk about big lumps of things. So this is the way I remember which one's which one uses a little n and which one uses a big N, is maybe conservation of size of letters. This one has a capital letter and a lowercase letter, and this one also has a capital letter and a lowercase letter. So we'll just leave it at that right there, and then I'll go into Charles's law and stuff like that. Kind of bouncing around on each other. And an ideal gas means two things. One, they do not interact with each other. So here we go. No interactions. Today we're really going to get into the idea of thermodynamics. So I want to talk first about what a state is. So, you know, even before that, perhaps I should define something called an ideal gas. Molecules don't take up space. So this lets us do all kinds of, you don't want to mess with regular gases when there are ideal gases around. An ideal gas is a gas, well, you know, a gas is molecules of stuff. And not only that, but not only do these particles not really interact with each other, I mean, they're going to hit the walls, but they won't really hit each other, but also they don't take up any space at all.